clearly outperformed its Swedish rival in terms of military capabilities during the competition held by Canada in 2021.
Have you ever wondered how a single-engine fighter jet could suddenly outperform aircraft that cost 3 times as much? Imagine NATO analysts seeing data that just didn't make sense. Jets performing beyond expectations, heat signatures lower than stealth fighters.
There's nothing close in capability between a Gripen and an F-35.
An acceleration that seemed almost impossible. Could it be a secret technology, a hidden upgrade, or something far more clever? For months, the changes went unnoticed, quietly reshaping how one of Europe's most affordable jets could operate in combat. Engineers were working behind closed doors, making adjustments so precise that even satellite and radar systems struggled to measure them. Every new report added to the confusion, leaving experts scratching their heads. Today we're diving into exactly what happened. Keep watching as we uncover how Rolls-Royce silently modified the Gripen, and why NATO didn't see this coming. For a long time, the Saab Gripen was seen as a smart and cost-effective fighter jet. It offered strong performance for countries that wanted modern capability without paying F-35 prices. But quietly, something began to change behind closed doors. The shift was so unexpected that when new data appeared inside NATO system reports, analysts were first confused, then surprised, and eventually concerned. The change traced back to Rolls-Royce. Most people know the brand for luxury cars, but its aerospace division is one of the leaders in aircraft propulsion. The upgrade effort began quietly after Swedish engineers realised the Gripen E could not reach its full capability unless its engine systems were heavily refined. Even though the jet still uses the GE-built F414 engine, major internal elements were redesigned with Rolls-Royce support. This included airflow channels, heat management layers, control software, and extremely tight mechanical tolerances. NATO was unaware this cooperation was happening, and Sweden chose not to publicise it because the upgrades would significantly change how the jet behaved in combat. The first major improvement focused on heat management. Modern fighter aircraft are tracked not only by radar, but also by infrared sensors carried by satellites, drones, and long-range missiles. By restructuring how heat moved through the engine, Rolls-Royce helped lower the Gripen's thermal output far beyond what is typical for a single-engine aircraft. When NATO test systems picked up unusually low infrared readings, analysts initially suspected faulty equipment. Sensors were recalibrated, but the results stayed the same. A single-engine jet was producing heat levels closer to those of stealth aircraft with 2 engines, which immediately drew attention from NATO intelligence teams. The second improvement involved fuel efficiency. By redesigning internal airflow paths, engineers reshaped the fuel burn curve. As a result, the Gripen E gained much greater range, reaching endurance figures that normally require twin-engine designs. This made the aircraft especially appealing to countries like Canada, where long-distance patrols over Arctic regions are necessary. Analysts were taken aback that a jet much lighter than the F-35 could cover nearly the same mission distance, while offering greater flexibility and lower operating costs. The third major change was digital. Rolls-Royce helped introduce a new engine control model that allowed the power plant to adjust thrust far more quickly. This gave the Gripen E extremely rapid acceleration. Pilots reported that the aircraft surged forward in ways they had never experienced before. During air combat simulations, this caused serious issues for older NATO interceptors. Sudden changes in speed made the Gripen harder to track during sharp manoeuvres. Sweden kept these findings quiet, but NATO later gained partial access to performance data, enough to understand that the aircraft had advanced well beyond its earlier category. What truly unsettled NATO was not one upgrade on its own, but how all of them worked together. Lower heat output, longer range, faster throttle response, and much higher survivability were all achieved without altering the engine's external design. On paper, the jet looked unchanged. When NATO's Technical Review Committee examined Sweden's updated performance logs, they realised something unusual had occurred. A single-engine fighter had reached the same general performance level as far more expensive stealth aircraft, without the heavy maintenance demands or sensor weaknesses that often come with them. Several NATO members quietly requested explanations from Sweden, but official responses remained vague. The reality that Rolls-Royce had quietly reworked the most sensitive internal engine systems only surfaced later through internal documents. By that point, the Gripen E had already become something new, a relatively affordable fighter that could challenge aircraft costing several times more. At first, NATO officials suspected the updated performance data had been altered. The numbers did not line up with what they believed a single-engine jet could do, but satellite tracking, infrared sensors, and AWACS radar all confirmed the same results. It became clear that major changes were happening out of public view. What NATO still didn't know at that stage was that Rolls-Royce had added a new airflow pressure control system inside the engine. This allowed the Gripen to maintain very stable thrust at high altitudes. Because of this, the aircraft could climb faster, operate higher, and consume less fuel at the same time. These traits are usually associated with heavy stealth aircraft or advanced twin-engine fighters. The system worked by redistributing tiny pressure changes using internal vanes that reacted within milliseconds. These parts were not visible from the outside and did not require any updates to official specifications, but their impact was massive. Pilots reported that the Gripen felt far more stable at extreme altitudes, allowing it to intercept targets that some larger NATO aircraft struggled to reach quickly. This alone sparked internal discussions about whether NATO's interception strategies needed revision. Another concealed upgrade involved engine noise reduction across specific frequency ranges. This was not about reducing sound for human hearing. It was designed to interfere with acoustic tracking drones used on modern battlefields. Rolls-Royce altered internal components so the engine produced fewer, consistent sound patterns. This made it much harder for autonomous drones to pinpoint the aircraft using audio data. NATO's drone warfare units tested simulated Gripen profiles and found that the jet could pass through certain drone defense zones without being flagged as a high-priority threat. While these discoveries already unsettled NATO, what followed caused even more concern. Rolls-Royce engineers helped integrate an adaptive thermal monitoring loop into the Gripen's digital engine controller. This system tracked heat buildup in real time and automatically rerouted cooling paths moments before hotspots developed. In combat conditions, this made the aircraft far more resistant to infrared-guided missiles. Older NATO jets often required pilots to manually manage throttle settings to reduce heat output. The Gripen now handled these adjustments on its own. On infrared displays, it could fade in and out at irregular intervals, making missile lots far harder to maintain. Sweden had kept these capabilities hidden, even from much of its own political leadership. Only a small group of technical experts knew the full details. This secrecy began causing friction when several NATO members started asking direct questions. Why was the Gripen performing far better than expected? Why did some of its sensor data look similar to that of stealth aircraft, even though it had no stealth coating? And why did Canadian evaluators record acceleration behavior that didn't match GE's published engine data? Over time, NATO analysts uncovered signs of Rolls-Royce involvement by comparing engine vibration data with known Rolls-Royce engineering signatures. Even though Rolls-Royce had not built the main engine, the tiny vibration patterns matched internal components commonly produced through the company's precision micro-engineering programs. This discovery raised a serious concern. If Sweden and Rolls-Royce could work together at this level without disclosure, other nations might attempt similar partnerships and sidestep NATO's normal oversight of fighter development. Behind closed doors, US officials warned that the Gripen was turning into an unpredictable factor. It was affordable enough for smaller countries to purchase, yet powerful enough to challenge heavily protected airspace. Because the upgrades were internal and not visible, standard export control systems could not properly monitor them. For the first time, NATO began to realize that the era of costly stealth aircraft dominating global air power might be fading. This shift had not been triggered by a massive arms race, but by Rolls-Royce quietly modifying the core of a single-engine fighter. While NATO tried to understand how the Gripen's performance had changed so quickly, Sweden and Rolls-Royce were already developing the next stage of internal improvements. These updates focused less on raw engine output and more on survivability, deception, and automated threat response. These were areas where even advanced NATO aircraft still depended heavily on external pods and bulky add-ons. Because of the Gripen E's modular design, these systems could be built directly into the engine control framework. This allowed the aircraft to function as one unified system instead of separate components working independently. One of the most unexpected advancements came from a digital synchronization process introduced by Rolls-Royce. Modern fighter jets produce vibration patterns that enemy sensors can use to identify aircraft types from long distances. Rolls-Royce developed software that slightly adjusted internal engine micro-vibrations based on altitude, speed, and threat conditions. As a result, the Gripen E could imitate the vibration patterns of different aircraft categories. During simulated combat exercises, some NATO radar systems initially labelled the Gripen as a drone, then as a trainer aircraft, and only later identified it as a fighter. This inconsistency disrupted threat classification systems that depend on stable vibration databases. Another major improvement involved the use of microburst cooling pulses. Instead of releasing heat in a smooth and predictable pattern, the modified engine released small, irregular bursts of cooler exhaust. This confused infrared tracking systems. Missiles that normally locked onto a steady heat source struggled to maintain guidance. In NATO's internal simulations, this change increased the Gripen's survival rate by as much as 40%. What concerned analysts most was that this advantage required no special materials and no stealth coatings. It relied only on intelligent engineering within the engine itself. As intelligence reports grew, some NATO engineers began asking a difficult question. If Rolls-Royce could achieve this level of improvement on a smaller and relatively affordable fighter like the Gripen, what would happen if other nations requested similar, quiet upgrade programs? Countries with limited defense budgets could suddenly field aircraft with performance close to top-tier NATO fighters. This risked weakening not just the technical balance, but also the political influence tied to selling expensive Western aircraft. At the same time, Sweden noticed a clear change in global interest. Nations that had once dismissed the Gripen as too light or basic began asking discreet questions about its upgraded versions. Several air forces requested demonstration flights, but were denied access to the most advanced internal setup. Sweden understood that the Gripen was no longer just another fighter jet. It had become a powerful asset, capable of shifting regional power dynamics. Even within NATO, some members privately questioned whether Sweden's growing technical independence could one day strain alliance unity. The situation escalated when a classified NATO briefing revealed that the Gripen's updated acceleration performance exceeded predictions from secret US simulation models. This meant American analysts, despite extensive modelling, had failed to predict how the internal upgrades would translate into real-world results. The report warned that NATO must now assume the Gripen could perform manoeuvres previously believed impossible for a single-engine aircraft. Some officials suggested creating new training programs specifically designed to counter the Gripen in close combat scenarios. Throughout all of this, Rolls-Royce said nothing publicly. There were no press statements, no technical disclosures, and no acknowledgement of involvement. Inside NATO, however, it was clear that Rolls-Royce had changed the way fighter aircraft could evolve, not through major redesigns or massive budgets, but through carefully concealed improvements inside the engine core. What made the situation even more ironic was that Sweden had never intended to challenge NATO. Their objective was straightforward: build a fighter that delivered strong performance, reliability, and independence without relying fully on US technology. Yet in doing so, they unintentionally exposed weaknesses in NATO's own aircraft philosophy. For the first time, Western defense planners had to think seriously about a future where flexibility, adaptability, and silent internal upgrades could matter more than sheer size or cost. NATO meetings turned from technical curiosity into policy sessions. Analysts in Brussels began to map where this kind of hidden improvement could cut across alliance rules and export licensing. Publicly, the Gripen E is sold and marketed with the American GEF 414 engine, a well-documented workhorse used on several modern fighters. That fact mattered. US export controls and end-use clauses attached to engines and some avionic components. A single-engine platform that relied on US propulsion could still be easier to track than one built from largely European parts, simply because export clearances are a point of legal and diplomatic visibility. As a result, whispers about replacing or offering alternative power plants began to make sense in procurement circles. Saab and several European firms have publicly discussed alternatives and export flexibility. And analysts point out that a European supply chain could reduce political friction for buyers who want fewer US strings attached. That said, technical reality is blunt. Swapping a jet's core engine is not a plug-and-play task. It requires redesign of mounts, fuel and air interfaces, cooling systems, and flight control software. It also changes weight, balance, and maintenance logistics. Industry sources and defense specialists repeatedly note that re-engining programs are major engineering projects that take years and significant testing. This makes the kind of rapid, covert transformation described in some forums unlikely without clear documentation or leaks. Rolls-Royce, meanwhile, is a visible player in military propulsion in Europe. The company continues to support and upgrade the EJ200 family used by Typhoon operators and invests in research on power, thermal management, and sustainment. That profile explains why a rumour mill would attach the Rolls-Royce name to any whispered Gripen upgrade. The company has depth, scale, and reason to work on thermal and reliability problems across many platforms. But public Rolls-Royce material and contracts show activity on engines like the EJ200. They do not prove secret modifications inside a GEF 414-powered Gripen. What NATO could verify, and what it did verify, was less dramatic but still important. Sensor logs and flight tracks published in narrow technical summaries show that some Gripen flight trials produce lower infrared signatures and fuel consumption profiles better than earlier blocks. In procurement terms, that can come from software tuning, new coatings, auxiliary heat routing, and improved mission planning, not necessarily wholesale hidden hardware swaps. In other words, meaningful gains can be achieved by a series of focused engineering improvements, rather than one single covert overhaul. That technical nuance fed two opposing interpretations inside alliance walls. One group argued that the Gripen's gains were the result of legitimate incremental upgrades, better FADEC maps, improved thermal insulation on hot sections, advanced flight management logic, and updated cooling ducts. These are the kinds of changes aircraft integrators routinely make during block upgrades and sustainment packages. The other group feared that something larger had slipped past normal oversight, whether a third-party module, a foreign microsystem, or a set of black box algorithms that met in the engine control domain. Both views forced NATO to widen its audit of test data and to press for more transparency in future export notifications. On the diplomatic front, Sweden took a careful path. The country reminded partners that the Gripen program is a national project with export rules consistent with Swedish policy. Saab emphasised the E-Series baseline features and the role of approved suppliers in upgrades. Where customers asked for lower dependence on US engines, Saab and European partners discussed longer-term industrial options, an expected, slow process rather than an instant switch. Public sales activity, recent deals and negotiations show that demand for Gripen remains steady, but prospective buyers are increasingly sensitive to supply chain transparency. Behind the scenes, engineering teams across 3 nations sketched 2 realistic paths for the Gripen line. Path 1. Continue incremental refinement around the F414, software updates, better heat routing, and aftermarket thermal management packages that preserve fit, require limited airframe changes, and keep warranty and logistics aligned with GE and Saab. Path 2. Pursue a long-term re-engineering project based on a European core, technically feasible but costly and slow, and likely to require new agreements on maintenance, lifecycle support, and export checks. Industry insiders told analysts the first path is by far the cheapest and fastest route to improved performance. The second is strategic and political, not merely technical. NATO's practical answer was procedural. Instead of assuming intent, alliance technical boards expanded their testing protocols and requested more detailed supplier disclosures for certain upgrade areas, thermal control, engine control software changes, and vibration signatures tied to new micro-components. That approach aimed to preserve operational security for manufacturers, while giving alliance procurement offices the data they needed to approve or flag new configurations. It also served as a warning. If manufacturers wanted to sell to alliance members, they would face more questions on provenance and test evidence. For industry, the episode became a commercial argument. Saab could sell a more attractive package if it offered lower lifecycle cost, simpler logistics, and clearer export paths. For engine makers, the moment was an opportunity to pitch modular upgrades that deliver measurable gains without forcing an engine swap. Rolls-Royce and other suppliers can credibly sell services that improve thermal management, control logic, and sustainment, all legitimate lines of business that would not require secret engineering inside a foreign-built core. Public contracts and press releases from relevant firms show continued investment in those areas. If the story has a lasting effect, it is this: modern fighters are becoming systems of systems. Engines, sensors, software, and mission planning interact in ways that can produce outsized improvements when integrated tightly. That integration sharpens the business case for close industrial partnerships, while at the same time raising questions about how alliances track and approve those partnerships. For NATO, the Gripen episode pushed a simple policy shift, more forensic testing, and clearer supplier traceability for critical propulsion and sensor changes. For manufacturers, it highlighted a market. Buyers want capable fighters without hidden strings and with transparent support chains. If you found this video helpful, make sure to like it and share your thoughts in the comments. Don't forget to subscribe for more videos like this.